Hi, I'm Matthias Beck. I'm one of the authors of Computing the Continuous Discretely. And in this video, we'll start chapter 6. This is about magic squares, semi-magic squares, and the Birkhoff-von Neumann polytope. We'll start with an ancient mathematical subject. These are magic squares. These are n by n squares. If you want square matrices with distinct entries, of consecutive integers, so every integer between 1 and n squared will be there exactly once. And then the magic condition, which says that each row, each column, and each diagonal sums to the same number. So for example, on this oldest magic square you see here on the left, we have the sum of these three integers in the first row and the sum of, let's say, this diagonal are equal. They're both 15. And you probably know that in this setting you can find sort of a formula for the magic sum, for the value of this sum that has to be equal. Anyway, so here's the question I would like to ask. You will not be surprised by this question. So, how many magic squares are there for a given size n? And this question is open for n equals 6. Let me show you the state of the art. This is the online encyclopedia of integer sequences, famously put together by Niels Sloan. And here you can see the first 5 numbers. So these are the number of magic squares up to rotation and reflections. So for n equals 3, it turns out there's exactly 1. For n equals 4, there's 880. And for n equals 5, there's more than 275 million. And if you can compute this number for n equals 6, you'll be quite famous. So this is a hard question. Let's make it easier. So we're going to ease the restrictions. I'd like to study a similar flavor problem, but use just enough restrictions to make this problem, number 1, interesting still, and number 2, at least approachable. So the first thing we're going to get rid of is distinctness requirement. And I will also get rid of, for now, the diagonals. Although in chapter 6, we see some results where the diagonals are considered. At the same time, you can see in this chapter that the question of counting sort of quote-unquote magic squares with these easier restrictions is quite different whether or not you consider diagonal constraints. At any rate, I want you to realize that we have linear constraints, sort of sums being equal, or maybe equal to some constant, or as we will do it, equal to some parameter, are polyhedral. And the same thing goes sort of with constraints where my entries are from. So if I don't say I need the numbers 1 through n squared, I will say simply that my entries are, let's say, non-negative integers. And again, this non-negativity is a polyhedral constraint. And so this gets us to the following sort of easier definition. We will study, it's called semi-magic squares. So again, these are n by n squares. We have integer entries, and let's say they are non-negative integers. And as I said, we have row and column sums still equal. So I'm forgetting about the diagonal, and I will set them equal to some parameter t. This is a positive integer parameter. So on the left you can see an example. This is a semi-magic 3x3 square, and I guess the parameter t here is 3. And you can see diagonals don't necessarily have to add up to this parameter. So, same question as before. I would like to know how many semi-magic squares there are. But now this is depending on this parameter t, so this becomes a counting function. And for some reason in the literature, we use h sub n for this counting function. This is the number of such squares. This should look familiar because many videos ago we studied contingency tables. You might remember my dogs and cats with fur and hair. And back then there was this funny counting function that I called h2, and now you know why I call this h2. These are precisely semi-magic squares with a parameter t. I already hinted at that we have polyhedral constraints. So this counting function is an Erhard counting function. Turns out this is an Erhard polynomial. So what's the polytope behind Hn? Well, here it is. We have n by n matrices. If I want to do polyhedral geometry, I need to be in real space. My constraints are all my entries of these matrices are non-negative. And then if you think of t as sort of a dilation parameter, then what I originally want is I want my row and column sums to be 1. If this polytope now gets dilated by t, this 1 gets replaced by a t, and I'm going to count integer lattice points. This will be precisely the Erhard polynomial. And this in turn is a famous polytope, the Birkhoff-von Neumann polytope. I already said this is sort of an interesting polytope on its own merits, because the matrices in here, they're called doubly stochastic matrices. And you can easily think of a reason. So we have sort of entries that might be probabilities. And what we're saying is these probabilities have to sum to 1 for each row and each column. I invite you to think of this polytope for a little bit. So for example, you might want to figure out that the dimension of this polytope is n minus 1 squared. And it's clear we have some equalities here, so it will not be a full dimensional polytope, but I claim the dimension goes down by exactly 2n minus 1. Slightly less trivial is the fact that the vertices of this polytope are the n by n permutation matrices. Yeah, so a permutation matrix is a 0-1 matrix with exactly 1, 1 in each row and column. And so each permutation matrix is in this polytope, and I claim those are precisely the vertices. So this gives already a hint that this polytope is quite non-trivial, because there's n factorial vertices. This is an exponential number of vertices in the parameter n, whereas my dimension only grows quadratically. It also gives you a hint that this is a polytope with many more vertices than facets. And I invite you to think about exactly what the facets look like. But okay, so this has a nice consequence. Permutation matrices are 0-1 matrices. So this means that the Birkhoff-von Neumann polytope is an integer polytope. And so now you know why I talked about the Erhard polynomial on the previous slide. So we know for integer polytopes, this lattice point counting function is a polynomial. There's one more concept that we know already that applies here. Let's look at the interior of the Birkhoff-von Neumann polytope, the relative interior. So how is this defined? Well, the only inequalities that I have are the inequalities on the coefficients. So now we're saying each entry has to be strictly positive. And I claim if you now look at a constraint, let's say sum over j. So if I have a constraint like this in the dilated polytope, so my sum is equal to t, and let's say my entries are integers, so I'm looking at the Erhard polynomial counting function. And what I have in here are n summands. And this is a uniform event. So I have the same thing happening for all of my constraints. And I claim what that means is, this is like from basic combinatorics, going from the solution space for all positive integers to going to the solution space for all non-negative integers is sort of a shift by n, because I can think of sort of adding 1 to each variable. And so this means for my Erhard polynomial, the integer point count for the interior, for the relative interior, is the same as the integer point count for the polytope, where t is shifted by n. And we've seen this, so this says that Bn is a Gorenstein polytope. Index n. So in particular, this also means that the h star polynomial, so this is the numerator polynomial of the Erhard series when I write it as a rational function, is palindromic. Or if you think of reciprocity, this really belongs to this line over here. So reciprocity now, if I apply this to my original counting function that I called hn, then reciprocity says that if I plug in negative t into hn, which is really just plugging a negative t into the Erhard polynomial, which we know up to a sign gets me the Erhard polynomial of the interior of the Birkhoff-von Neumann polytope, and the sign depends on the dimension. Turns out negative 1 to the n minus 1 squared is the same as negative 1 to the n minus 1. At any rate, so now I'm at the interior, and the Gorenstein condition now says this is hn of t minus n. So these Erhard polynomials have a special symmetry. It's the symmetry given by this Gorenstein condition. Let me finish with just a small afterthought, and I will just concentrate on the case n equals 3. So here the dimension is 4, so that's the degree of h3 of the Erhard polynomial of B3. So we're in a situation where we have a 4-dimensional polytope living in 9-dimensional space, so we have just about no way of drawing a picture of this situation. But I claim we can easily compute the Erhard polynomial from what we know so far. So let's see, we have, so I'll write h3 for this Erhard polynomial. We know h3 of 0, constant term is always 1, of an Erhard polynomial, but we also know h3 of 1, so I claim in the original polytope the only lattice points are the permutation matrices, of which there are 3 factorial, which is 6. But by what we just said, you can think about this also from first principles. The evaluation h3 of negative 1, which is the number of interior lattice points, I claim is 0. This comes also from the Gorenstein condition, but again, you can think about this just from first principles. And the same thing holds true for h negative 2, so the number of interior points in twice the polytope. And so here comes the Gorenstein condition, and again, you can think about this from first principles, but the Gorenstein condition now says that h3 of negative 3 is the same thing as h3 of 0, up to a sign which in this case is plus 1, so we get another 1. And so these are 5 evaluations of a polynomial of degree 4, and these 5 evaluations determine a polynomial. I can now do interpolation, and if you do that, you're welcome to try this out. I recommend a computer. You will find this quadratic polynomial for h3. So now we can ask the question, what about larger n? And I'd like you to realize this, what I did here is not as easy anymore as n grows larger. Because what we need is, we need something like n minus 1 squared evaluations. And of course this becomes harder as n increases now. You could certainly compute this almost by hand for n equals 4 still. And then for n equals 5 and 6, you might want to use a computer. And at some point, soon thereafter actually, you will realize that your computer will give up on you, actually. And so we'll need some new ideas for this, some ideas other than interpolation. And that's what we're going to do in the next video.